Hello everyone, welcome back to Through Deviations. In today's video, we are going to be defining the definite integral. We're going to talk about some evaluation strategies. And this video is going to get a little bit technical today because we're going to be dealing with a lot of sigma notation. We're going to be dealing with a lot of limits. It's going to be kind of like our first video on differentiation where we need to deal with that limit with the difference quotient. So we're going to be talking about that kind of stuff today. And don't worry, this might seem a little bit intimidating, but there are going to be much easier ways to evaluate an integral, and we will be covering that very soon. All right, so let's get started by defining the definite integral. This is something that I touched upon in the last video, but we're going to do it one more time. And we're going to use our new notation. So the limit, as n approaches infinity, of the sum from I equals 1 to n of f of x sub I times delta x is defined as the definite integral between a and b of f of x dx. All right, so what is this saying? So if I have the integral sign, I have the a and b. So the a and b are called our bounds of integration. And it's super simple. A and b are just the start and endpoints of where we want to calculate area under a curve. So if I have a definite integral of f of x from a to b, then that's going to be the area under the curve between a and b. Then we multiply it by this little guy dx here, and that's called our differential. And we can think of that as the width of the little rectangle that we are summing up. But it's probably going to be also very helpful to think of that as telling us what we are integrating with respect to. So if we have a dx, that means we're integrating with respect to x. If I have a dt, then we're integrating with respect to t. So as I said earlier, we will integrate from a starting point to an ending point, and our answer is going to be the area underneath the curve between a and b. Some important definitions that we can cover are, first, our delta x value. So our delta x value that we have in the sum here is going to be b minus a over n. And then our x sub I, the thing that we've got in here, is a plus I times delta x. And just one more thing to define called a Riemann sum. So the Riemann sum is just this sum in here. So this is the Riemann sum, and this is a tool that we can use to approximate the integral. It will give us more control over how we approximate it as well, with the number of rectangles and where we take the sum from. So as I said in the couple of videos ago, when I'm doing a Riemann sum, I can kind of have three different cases. I can have one case, let's call this the left-hand case, where the rectangle touches the function on the left-hand side. I can have the midpoint case, which we'll talk about in the next video, where it touches in the middle of the rectangle. And then I can also have the right-hand case, where the rectangle touches the function on the right-hand side. So those are three cases, and you can see that these will give us different values, because some overlap the function, some don't cover the function enough. We've got a lot of differences in there. Similar to differentiability, we also have integrability. So integrability basically says that if a function is continuous on the interval between a and b, or it has finite jump discontinuities, then we can integrate the function f. So when I say that we have finite jump discontinuities, well, that means that if I have a function that looks like this, and I have jumps on my function, this would be a piecewise function likely. Well, this just means that I can divide this into 4 sections, or depending on how many jump discontinuities you have, and then I can just take 4 integrals. I can take one integral there, I can take one integral there, I can take one integral in here, and I can take one integral in here. And it's just finite because we can't divide it infinitely many times and then reasonably integrate all of those times, of course. All right, so we talked about that notation a couple slides ago. So now we're going to talk about converting between summation form to integral form. So we are going to convert the limit as n approaches infinity of the sum from I equals 1 to n of x sub I plus x sub I times the natural log of x sub I times delta x on the interval between 3 and 5. So immediately we should see the interval that we are integrating over, and that means that we are going to have our lower bound as 3 and our upper bound as 5. Then if you remember, in here we put our function, and here we put a dx. So here we have our function, and our dx we can just write at the end. So this will become the integral from 3 to 5 of x plus x times the natural log of x dx. And we can drop the sub i's as well when we put it into integral form. Let's practice an evaluation of one of these guys. So this is probably where it's going to get a little technical. We're going to try integrating the x cubed minus 6x from 0 to 3. So to do this, if we remember, for that Riemann sum, we have from I equals 1 to n of f of x sub I times delta x. So we need to know our x sub I, and we need to know our delta x. So our delta x is just going to be b minus a over n. So the difference between 3 and 0 is going to be 3. And we divide that by n. So it gives us 3 over n. And x sub I is equal to a plus I times delta x. So this is just going to give us 3i over n, because a is 0. All right, so now let's try to evaluate this guy. So we need to put this into our Riemann sum and tack on the limit as well. So that's going to give us the limit as n approaches infinity of the sum from I equals 1 to n of f of 3i over n times 3 over n. Let's take out that 3 over n, and we are going to put our function in there as well. That's going to give us n, the limit as n approaches infinity of 3 over n times the sum from I equals 1 to n of 3i over n cubed minus 6 times 3i over n. Let's continue to simplify. We're working towards something where we can evaluate this sum, and that's going to come from our sigma formulas that we talked about in the last video. It's going to give us the limit as n approaches infinity of 3 over n times the sum from I equals 1 to n of 27 over n cubed times I cubed minus 18 over n times I. More simplification will allow us to evaluate these sums. So if we remember, we know the sum for I cubed and we know the sum for I. So it's going to give us the limit as n approaches infinity of 84 over n to the 4th times the sum from I equals 1 to n of I cubed minus 54 over n squared times the sum from I equals 1 to n of I. Of course, now that we know these sums, we can evaluate the limit. So that's going to give us the limit as n approaches infinity of 81 over 4 times 1 plus 1 over n squared minus 27 times 1 plus 1 over n. And of course, these 1 over n's go to 0, and we are going to be left with negative 27 over fourths if we evaluate this, which is fairly easy. All right, so now that we've tried an evaluation of an integral, maybe let's try to figure out some properties to make it a little bit easier on ourselves. So let's look at some properties. So we have what I call the sine rule. This basically means that if I switch the bounds, it's going to be the negative of the original. So the integral from a to b of f of x dx is going to be equal to the negative integral from b to a of f of x dx. It's a pretty easy property to understand. We also have the constant evaluation rule. This basically means that if I take the integral from a to b of c dx, it's going to be c times b minus a. This is a form of one of the very important theorems in calculus called the fundamental theorem of calculus. This is going to make it really easy to evaluate integrals. We're going to talk about that in a couple of videos. It's going to make your life really easy. Another rule that we have is the separable sum rule. So we can separate integrals of sums and differences of functions. So if I have the integral from a to b of f of x plus or minus g of x dx, that's equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. Finally, we have the constant multiple rule for the integrals. This basically means that if I have a constant multiplied by the function that does not depend on x, then I can take out that constant and put it outside the integral. So we have the integral from a to b of c times f of x dx is equal to c times the integral from a to b of f of x dx. Now that we know these properties, and you might notice we don't have as many properties as we did with differentiation, now we're going to talk about using these properties. So we are going to try to evaluate this guy. So to show you what I'm doing here, I've got the answer down here, but why don't we follow along with what I'm doing? So you have the integral from 0 to 1 of 4 plus 3x squared times dx. Right, so what we learned in the last slide means that we can take the integral from 0 to 1 of 4 plus 3x squared dx, separate it into two integrals. So we have the integral from 0 to 1 of 4 dx plus the integral from 0 to 1 of 3x squared dx. So let's deal with this guy first here. We'll deal with this one. So we'll take the integral from 0 to 1 of 4 dx. We talked about that constant evaluation rule. So if I have the 4, 4 times the difference of the bounds, and that's going to be 4 times 1, which is 4. If I take the integral from 0 to 1 of 3x squared dx, we can take out the 3. It becomes 3 times the integral from 0 to 1 of x squared dx. Again, we proved that this was equal to, this guy here was equal to 1/3 in our first video for integral calculus. So we proved that that's equal to 1/3. Go back and watch that if you don't remember. And we multiply that by our constant here of 3, and that's going to give us 4 plus 1 if we bring this guy here, and then that's going to be equal to 5. So that is our final answer for the integral from 0 to 1 of 4 plus 3x squared dx. In the next video, we are going to be back to talk about a few more properties, and then we are going to be talking about the fundamental theorem of calculus. It's going to make it a lot easier to evaluate these integrals. What we did a couple slides ago was probably not fun, but getting that done is something that is very important to a calculus student. All right, we will see you in the next video to talk about some more properties.